The standard Collatz conjecture is a notorious mathematical landscape. It operates on an infinite scale, defined by stochastic uncertainty, where data trajectories scatter with apparent randomness. Take any starting number, and it will undergo a series of unpredictable crashes, dividing wildly before bouncing back up. Standard mathematical tools fail to find order here because there is no discernible rhythm to these impacts. When a path behaves with pure, unconstrained randomness, mapping an infinite sequence becomes a mathematical impossibility. The data branches out endlessly. We cannot solve infinite randomness simply by observing it. We have to physically reshape the environment these numbers exist within to force an answer. To do this, mathematicians rely on the Modular Collatz problem. Instead of letting numbers run off into infinity, this method wraps the chaotic path around a finite clock of a specific size, known as M. By translating the math into an all-odd environment, we skip the even numbers entirely. This bypasses the unpredictable crashing behavior seen in standard number theory. Lifting the map into this finite ring transforms the behavior of the system. Stochastic chaos is replaced by a deterministic repeating clockwork. The question becomes how we isolate these exact repeating patterns. To do that, mathematicians use a method called the Three-Tier Sieve to force infinite paths into precise closed loops. By constructing these all-odd circuits, we identify the modular wrap. This is the geometric overflow, the moment the math exceeds the clock size, that permits periodic closures to exist as legitimate physical states. Achieving this order requires a process called the Information-Loss Cascade. To find the structural fingerprints of these loops, we have to purposefully delete the vast majority of the raw data. This flowchart visualizes that compression. On the left, it starts with a sprawling network representing the messy, infinite trajectories of physical reality. As we funnel down through the pipeline, we shed state sequences until we reach a minimal boundary vector, compressing all the way down on the right to a single isolated variable known as the winding coefficient, or K. Despite losing all that raw data, a mathematical principle called the no-collision theorem proves that this final winding coefficient is a perfect hash. It encodes the path's entire internal history, preserving its unique DNA without storing the explicit steps. This single coefficient acts as a structural anchor. It mathematically locks the start and the end of a trajectory onto a precise intersecting hyperplane. Shedding the bulk of infinite mathematical data is the only way to cut through the noise and isolate the exact arithmetic alignment of a given path. Inside this system, the mechanical engine is driven by a constant tug-of-war, governed by a measurement known as the winding weight vector. This line chart maps the first force in that tug-of-war. Early in a sequence, a process called three-adic expansion heavily amplifies reductions across the cycle. This drags the structural weight of the path downward into a distinct V-shape. Then, the competing second force takes over. At the end of the cycle, a mechanic called two-adic denominator clearing dominates, causing pure exponential growth that drives the line sharply upward. This engine, however, has a hard physical limit known as the even density obstruction theorem. For any sequence to survive, the density of its even steps must remain below exactly 36.9%. If a trajectory's even steps exceed that 36.9% threshold, the clockwork engine stalls. The path loses the momentum to force a closed loop. Even when the engine runs perfectly, the physical constraints of the clock apply strict energy limits, starting with the Cooldown Law. When a number overflows the modulus, it releases massive mathematical energy, forcing the value down into the lower half of its domain. Because the number is physically forced so low, it is impossible for two modular overflows to occur back-to-back. This data table compares the impact of that physical restriction. Without the Cooldown Law, the unrestricted space grows exponentially to massive numbers. By removing the impossible back-to-back overflows, the search space is slashed down to the vastly smaller Lucas admissible count. When we look at cycle lengths from 3 to 6 steps, the output of this restricted space is highly constrained. The surviving loops are simple, symmetrical, and pure. But at exactly 7 steps, the system hits a bifurcation point. The expanding map overcomes the simplicity of the early periods, and an asymmetric sawtooth pattern emerges. This new pattern introduces a gap vector of 2 and 3. By balancing two distinct clusters of mathematical growth against two separate modular reductions, The rigid symmetry of the earlier periods is finally broken. The clockwork applies extreme physics-like limitations on numbers, yet within those exact rigid boundaries, it autonomously generates immense asymmetric complexity. Understanding the mechanics of the clockwork is one thing, but mathematicians must also prove these theorized loops physically exist. That requires a final test, passing through the ultimate arbiter, the coefficient automaton. The coefficient automaton is a scale-free mathematical recurrence. It acts as a strict security checkpoint that calculates the precise behavior of a trajectory step by step. This automaton validates whether a candidate sequence maintains the correct integrality and all-odd parity to safely survive the tight physical confines of the system's topological tube. Discovering a modular loop is never a theoretical guess. Every sequence must pass this strict scale-free physical validation to prove that it legitimately connects its start to its finish. The entire process rests on three distinct pillars. The first is arithmetic alignment, which guarantees that the start and end of a sequence intersect perfectly on a specific geometric hyperplane. The second is structural admissibility, where the strict energy limits of the Cooldown Law physically prevent consecutive overflows, drastically limiting the search space. The third is physical validation, relying on the automaton to guarantee that the sequence successfully survives its journey. The Information-Loss Cascade transforms this search into a scale-free coordinate system. By stripping away the chaos, it provides the tools needed to navigate infinite numbers. The infinite landscape of modular cycles consists of predictable, certified closures ticking perfectly inside an engineered architecture of numbers.